Hello world! In today's tutorial, we're going to add persistent memory using the pgvector extension for PostgreSQL to the LangGraph ReAct agent using the Tavily tool to get a web connection and a Mistral LLM. Using the pgvector extension for PostgreSQL allows us to store past messages as embedding vectors instead of strings and perform vector similarity search. This is a more efficient way of implementing persistent memory than using LangGraph's PostgreSQL checkpointer. PostgreSQL checkpointer always passes all past messages as a context, while using the pgvector for PostgreSQL allows us to pass only the n most similar past messages in case of implementing the limit vector similarity search type, or to pass only the past messages that meet a specified similarity threshold in case of implementing the threshold vector similarity search type. That will save us a ton of money by spending fewer tokens. I'll show you an example in Python. Before we start, I want to emphasize that the purpose of my tutorials is not that you code parallel to me. For this matter, I always upload the full code to my GitHub profile. You can find the link in the description below. Let's get to the point. If you haven't watched my previous LangGraph tutorial, please do so because this one is an upgrade of that one. It's mandatory because today we'll compare persistent storage implementation using LangGraph's PostgreSQL checkpointer with the pgvector extension for PostgreSQL. In the previous LangGraph tutorial, we implemented persistent memory to a LangGraph agent, but the way LangGraph's PostgreSQL checkpointer works is that it always passes all past messages as a context with every subsequent message, even if they're irrelevant. Let's look at an example from the previous Langsmith tutorial's README file. Just to clarify, this is a Langsmith tutorial. I strongly recommend you watch this one too, besides the previous LangGraph tutorial. Just so you don't get confused, these two are different. You can find links for both in the description below. In the previous Langsmith tutorial, we programmatically showed that LangGraph's PostgreSQL checkpointer does pass all past messages as a context with every subsequent message, even if they're irrelevant. Look, in the third chat session, we simply greeted the LangGraph agent with "Hi," and all the past messages were passed to the LLM as a context. Are they necessary for the LangGraph agent to greet us back with, "Hello, how can I help you today?" Absolutely not. What's the consequence? You spend more tokens and consequently pay more to the LLM provider. This is an inefficiency we'll solve today. The pgvector extension for PostgreSQL has been out for a while now. Using it, we can solve the inefficiency that exists in the case of using LangGraph's PostgreSQL checkpointer. I could only give you the solution, but I think it's important to understand what happens in the background. So there are a few concepts we'll go through briefly: embedding vectors, vector similarity search, distance functions, cosine similarity, and limit versus threshold-based approaches. First, what are embedding vectors? Computers don't understand words like we do. They only work with numbers. Embedding vectors help turn words, sentences, or even full paragraphs into lists of numbers that capture their meaning. For example, the sentence, "Subscribe to my YouTube channel," becomes a list of numbers, let's say 0.12, -0.45, 0.88, where each number encodes semantic information. How many numbers there are in the list depends on the embedding model used. Different models create embedding vectors with different dimensions. For example, Mistral's Mistral Embed creates 1024 dimensional embedding vectors, which means there are 1024 numbers in the list. You know, three-dimensional space? Well, this is a 1024 dimensional space, if you can imagine that. Second, what is a vector similarity search? If we ask a computer if the sentences, "I enjoy watching AI tutorials on YouTube," and "I love watching YouTube AI tutorials," are similar, it'll have no clue. If we ask a computer if their embedding vectors are similar, it'll say yes. But having text stored in PostgreSQL as embedding vectors is not enough for a computer to answer this question. It needs to perform a vector similarity search. It needs to compare two vectors to know if they are similar and how much. Third, what is a distance function? It's a mathematical function used for calculating vector similarities. When we perform vector similarity search, we use a distance function to do so. There are many distance functions. The pgvector extension for PostgreSQL we'll use today supports the following distance functions: cosine distance, L1 distance, L2 distance, inner product, Hamming distance, and Jacquard distance. In this tutorial, we'll use the cosine distance, which is a popular choice in the AI community. For all the nerds out there, this is the mathematical formula for calculating the cosine distance. I want to mention that while we'll leverage pgvector's operator for calculating the cosine distance, which is this one, we'll calculate cosine similarity, which can be calculated by simply doing 1 minus cosine distance. So, cosine similarity equals 1 minus cosine distance. Keep that in mind. Cosine distance and cosine similarity are two different things. Fourth, what is cosine similarity? We just explained it's derived from cosine distance and utilizes the cosine distance mathematical function to calculate similarity between two embedding vectors. But how do we interpret it? Cosine similarity can take values between -1 and 1, where 1 means the two embedding vectors are identical in direction, forming a 0-degree angle, indicating perfect similarity. 0 means the two embedding vectors are orthogonal, forming a 90-degree angle, indicating no similarity. And -1 means the two embedding vectors point in opposite directions, forming a 180-degree angle, indicating perfect dissimilarity. Fifth, what is the limit versus threshold-based approach? Assuming that we have vector similarity search results, we need to decide whether we want to choose a limit or threshold-based approach. In simple terms, do we always want to pass a fixed number of past messages as a context? Or do we want to pass past messages as a context dynamically? If we choose a limit-based approach, we'll always pass a fixed number of past messages as a context. For example, if we set the limit to 5, we'll always pass the top 5 most similar past messages to the latest user message as a context, along with the latest user message to the LLM. Here's a challenge with the limit-based approach. The limit-based approach might include messages that aren't very similar because we always pass the top 5 most similar past messages as a context along with the latest user message to the LLM, no matter how similar they are. Let's say our top 5 most similar past messages have the following cosine similarities. It makes sense to take the first and second most similar past messages, maybe the third too, but the fourth and fifth are not similar to the latest user message. But we're forced to include messages 4 and 5 even though they're not similar to the latest user message, just to meet our 5 messages limit rule. We're wasting tokens by doing this. You might ask, how can the fourth and fifth messages not be very similar if they're among the top 5 most similar? The limit-based approach is not flexible when the conversation topic changes. If the conversation with the LangGraph agent suddenly shifts from talking about dogs to talking about cats, we still pass the top 5 most similar past messages as a context to the LLM, even if only 3 of them are about cats. We can't adjust the number based on what's actually relevant. The limit is set to 5. If we choose a threshold-based approach, we'll dynamically decide how many past messages to pass as a context based on a similarity cutoff. Instead of always passing a fixed number, we only include past messages that meet a certain cosine similarity threshold. For example, if we set the threshold to 0.75, we'll only pass past messages with a cosine similarity score of 0.75 or higher as a context to the latest user message. This ensures that we only include relevant context and avoid wasting tokens on unrelated messages. The benefit? Remember the dogs and cats example we discussed when explaining the limit-based approach? If the conversation shifts from dogs to cats, we won't be forced to include barely relevant dog-related messages just to meet an arbitrary number. Instead, we dynamically adjust the context window to include only messages that are truly similar. However, a challenge with the threshold-based approach is that the number of included messages can vary. Sometimes we might have plenty of relevant messages, and other times we might have very few. This variability requires careful tuning of the threshold to balance relevance. Let's say we set a threshold of 0.75 for cosine similarity. Forget about our dogs and cats example and imagine we have the following cosine similarities. I intentionally set cosine similarities close. Should we set the threshold to 0.74 or 0.73 to include more past messages to the latest user message as a context along with the latest user message to the LLM? That's a challenge with the threshold-based approach. The best way is probably to try and see what works the best for your case. Now, that was quite a bit of theory, but everything we discussed is necessary for you to understand what we'll be doing in the next few minutes. Let's open the code editor. In the next few minutes, you'll see me typing commands without hitting enter or talking about creating something without actually doing it. That's because I already completed those steps while preparing for this tutorial. I just wanted to point that out so you don't get confused. Okay, let's set up our environment to be able to add persistent memory using the pgvector extension for PostgreSQL to the LangGraph ReAct agent using the Tavily tool to get a web connection and a Mistral LLM. Clone the repository. Change the directory to this one. Create a virtual environment named myvenv. Activate the virtual environment. Install the dependencies. Create an env file to set up your environment variables. You need to set the Mistral API key, the Tavily API key, and a few environment variables for PostgreSQL. Okay, I should mention that in this tutorial we'll use Mistral instead of Anthropic as we did in the previous LangGraph tutorial, but you can use any LLM provider you want. Just don't forget to adjust a few lines in the Python script. More specifically, lines 7, 8, 42, and 48. For PostgreSQL to work, we need to set environment variables for username, password, host, port, database, and SSL mode. I want to emphasize that these values should match the ones we'll set in the following steps. Yours could be different if you wish, but it's important that they match the ones you'll set in the following steps. Let's continue with the setup. Open a new terminal window. We need to pull the PostgreSQL Docker image and the pgvector Docker image. First, let's pull the PostgreSQL 16 Docker image. Before continuing, let's verify that the image has been pulled successfully. Success, we have PostgreSQL installed via Docker image. Second, let's pull the pgvector extension for PostgreSQL 16 Docker image. We want to pull the pgvector extension for PostgreSQL 16 specifically, as we pulled PostgreSQL 16 in the previous step. Once again, let's verify that the image has been pulled successfully. Success, we have pgvector installed via Docker image. Now let's run PostgreSQL with pgvector in a new container. Remember what I was telling when describing the env file? These values should match. Here we simply name the container pgvector, set the Postgres user password, set the port on the host machine that maps to the PostgreSQL port inside the Docker container, and tell Docker to take our Docker image that we just pulled and run it in this container. After you run this command, you should see a running container named pgvector in the Docker desktop app. Let's continue with the setup. Open pgadmin. We have to do a few things here. First, register a new server. Set the name of the server to whatever you want. Next, set connection parameters. The host name should be set to localhost. The port to 5433. Remember, we set that with the Docker command. The maintenance database to Postgres, the username to Postgres, and the password for the username to what you set with the Docker command. Click Save. Second, create a new database in the newly created server. Set the name of the database to whatever you want. This is one of your environment variables in the env file. Click Save. Third, enable the pgvector extension in the newly created database. Open the query tool and execute the command. Create extension vector. Be careful. It's just vector, not pgvector. The setup is done. Let's move on and take a look at the code. Okay, at the top we have a bunch of imports. The next few lines parse a terminal argument to choose a similarity search type. As we already discussed a few minutes ago, we can choose between the limit and threshold-based approaches. Whichever is chosen, we save it to a variable. Moving on, we load all environment variables from the env file. Also, we initialize rich for nicer output formatting and visualization. Regarding Mistral, we have two initializations. First, we initialize a Mistral LLM using a class from the LangChain SDK. To be precise, we'll use the Mistral large in this tutorial. Second, we initialize a Mistral client using a class from the Mistral SDK. Why do we have two initializations? You'll see in a minute. Then, we initialize the Tavily tool to connect our LangGraph agent to the web. Whenever the agent decides to use the tool, Tavily will return 3 results. After that, we have a function to process chunks from the LangGraph agent. There are quite a few lines of code, but essentially what's happening here is the following. Every time we ask the LangGraph agent a question, it will return one or multiple answers called chunks. If a chunk contains tool calls, we want to display in the terminal what tool was used and what query was passed to the tool. If a chunk doesn't contain tool calls, it means that that is the LangGraph agent's final answer to our question. Okay, we have the final answer. Now what? This is when we leverage the Mistral client. Remember the 2 Mistral initializations? The second one is used here. Why? We turn a string to an embedding vector with the Mistral Embed LLM. So we take the LangGraph agent's answer, transform it to an embedding vector, and insert everything in PostgreSQL. When saying everything, I mean inserting the role, the message, and the embedding vector of the message. After all this is stored in PostgreSQL, we display the LangGraph agent's final answer in the terminal. Next, we have the main function. We'll do a bunch of stuff here. It's necessary to connect to the PostgreSQL database using an async connection pool. Here's the connection string. As you can see, we utilize all the PostgreSQL environment variables from the env file. Only after we connect to the PostgreSQL database are we able to use it. Remember that we enabled the pgvector extension in pgadmin? Here we check if the pgvector extension is enabled. If not, we can do that programmatically too instead of using pgadmin. Also, we need to create a table named chat if it doesn't exist already. Mind that we can run the Python script over and over again and the table might already exist, so we need to check that. The table will have 4 columns: ID, a unique primary key, role, a varchar field for user roles, message, a text field for storing chat messages, and embedding vector, a vector 1024 field that stores a 1024-dimensional embedding vector. This is a dimension that the Mistral Embed LLM returns, so it matches. Moving on, we create a LangGraph ReAct agent. Remember the 2 Mistral initializations? The first one is used here as an LLM along with Tavily as a tool. Then we have a loop. The goal is for the user to be able to chat with the LangGraph agent. The conversation keeps going until the user decides to quit the chat. Next, we need to turn a string to an embedding vector with the Mistral Embed LLM as we did for the LangGraph agent's answer. But here, we do it for the user's question. The logic is identical. In both cases, we insert the role, the message, and the embedding vector of the message. The only difference is that we do it for the user's question instead of the LangGraph agent's answer. At this point, we perform an embedding vector similarity search. If we choose the limit-based approach, we'll always return the top 5 most similar past messages. Could be either past user questions or past LangGraph agent answers, stored in PostgreSQL, where similarity is calculated against the latest user message. Here's an SQL query that does that. What's cool is that we also remove any duplicates, meaning identical messages, if there are any, because we don't want any duplicates to be among the 5 returned messages. If we choose the threshold-based approach, we'll return all past messages, could be either past user questions or past LangGraph agent answers, stored in PostgreSQL that have a cosine similarity equal to or greater than 0.75, where cosine similarity is calculated against the latest user message. Here's an SQL query that does that. Again, we remove any duplicates. I want to emphasize that without the pgvector extension, we wouldn't be able to perform similarity search with PostgreSQL alone. Actually, the similarity search is performed here when we fetch results in an async manner. Also, we want to display similarity search results in the terminal. Building on that, we need to prepare similarity search results to be passed to the LangGraph agent. But before we do that, let's explain two types of messages: a human message and a system message. The human message is the user's question. We save it to a variable when a user enters it and pass it here. That's it. The system message is a list of similarity search results that will serve as a context to the human message. We iterate over the similarity search results and add them to the list. However, before adding the list of similarity search results as the system message, we need to make sure that there are any. With the limit-based approach, this is unnecessary because we'll always have 5 similarity search results. But with the threshold-based approach, it might happen that the latest user question is so much different than anything that was discussed with the LangGraph agent in the past that there will be no similar past messages returned, as none will reach the threshold that we set. In this case, we don't want to add the system message, just the human message. So if there are any similarity search results, we want to insert the system message at the beginning, index 0, of the messages list. Also, we want to display both the human message and the system message in the terminal. As with displaying similarity search results in the terminal, this is just for us to see in the terminal what's happening. Wrapping up, we asynchronously pass the messages list containing both the human message and system message to the LangGraph agent and wait for its response in chunks. If the LangGraph agent decides to use the Tavily tool, multiple chunks may be returned. As these chunks arrive, we process each one using the function we discussed earlier to extract relevant information. Finally, since the main function is asynchronous, we execute it accordingly using asyncio. Before we run the Python script, I want to mention that I spent hours documenting the whole setup process in the README file of today's tutorial. So, feel free to check it out and don't forget to star my repository. Now comes the fun part. We'll run the Python script. One more thing. I have to mention that I changed the Python script just a little bit to display calculated cosine similarities in the terminal. This was not implemented when we were taking a look at the code. Okay. Right now, I have 95 messages in PostgreSQL, both user and LangGraph agent messages. First, we'll run the limit-based approach. Let's ask the LangGraph agent what our name is. That's something Mistral LLM doesn't know, but I provided that information in one of my past conversations with the LangGraph agent when I was preparing this tutorial. As you can see, here are the top 5 most similar past messages with corresponding cosine similarities to our question, "What's my name?" These were passed as a system message for context, and this is how the LangGraph agent correctly answered our question. Let's quit this chat and clear the terminal. Second, we'll run the threshold-based approach. Let's ask the LangGraph agent the same question. Again, it's something Mistral LLM doesn't know, but information is available from past conversations. As you can see, here are 18 past messages with corresponding cosine similarities to our question, "What's my name?" So there were 18 past messages with cosine similarity equal to or higher than 0.75 compared to our question. Like before, these were passed as a system message for context, and this is how the LangGraph agent correctly answered our question. This is a way not to pass all past messages, but only the most relevant to implement a persistent memory to a LangGraph agent. This saves us a lot of money. How cool is that? That's it. Thanks for watching. If this tutorial was helpful, please like, comment, and subscribe.